All right, let's get started. Yeah, so last week we looked at monoids from a formal point of view, and we saw that unlike in Haskell, we can actually enforce some laws, and then we saw structure preserving transformations, homomorphisms between monoids, and then we're hinting at the fact that if you start studying structure, basically, in both like the objects and then the maps between them and so on, then there's a topic called category theory, which is the systematic study of these things. And then we sort of say that a category is a fancy monoid, but without saying anything more than that. And now today we're going to look at what it means. Yes.
You'll notice that the amount of funny Greek words may increase, but don't be put off. Actually, there's a Latin word that we ought to be using at this point, which is domino, right? Because categories are stuff that fit together end to end in a way where there's some kind of compatibility involved. They fit together like dominoes. If that means any, I mean, maybe dominoes are a thing of the distant past that people don't know about. But yeah, generally speaking, monoids are about glomming stuff together, but in this sort of indiscriminate, there's a single carrier set for a monoid, and any two things in it come together to make one thing. Oh, cool. Whereas if you refine that by saying, well, you know, things have two ends, and you can combine them if they meet in the middle. That's all that's happening, is that we're getting a bit more Lego kit. So yes.
We need to zoom in quite aggressively, be able to see this stuff, but...
Yes. But that's the thing is that we talk about the objects of a category. And the objects are the things at either end of a domino. And then we talk about the morphisms, although some people just say arrows. And those are the things which actually connect one end to the other. So in this picture, the numbers are the objects and the dominoes themselves are the morphisms. Right. And you can plug them together as long as the back end of one matches the front end of the next. And you've been doing this for years, right? Because you're used to functions which have input types and output types. And the input and output types are the objects, and the functions themselves are the morphisms, and they plug together if the types match. I mean, all that's happening is more of that, and then you start looking for more of it, and you find it everywhere. That's the main thing, is to get switched on to this structure so that it jumps out at you whenever it's around.
Yes, so the functions are a good thing to have in mind because they have this sort of structure, but they're also a false friend because they have a lot of properties that others don't, or they don't have properties that other examples have. So for dominoes, you can always flip the domino, right? And then if you can go from 5 to 4, you can go from 4 to 5 also. But it's not the case that you can flip all the functions necessarily. So it's good to have them in mind as an instance, but like remember that it's a very generic setup, and so there are more exotic things also in there. So zooming out a little bit. So why do we say it's a fancy monoid? Well, It's
Yes.
because of these things, right? So we have a unit morphism from the object to itself, but the important thing is the unit aspect, which should remind you of the unit of the monoids, of monoids in general. And then there's a way to combine two morphisms, so that should remind you of the diamonds in monoids. Of course, here, because we have types of objects and morphisms are between objects, then you can only combine things that make sense. So this is the domino example, right?
Yeah.
And then the unit, because you're not doing anything, the source and the target are the same, right? You're not moving in between any two things. I could
Yeah.
add.
Sometimes called the unit that identity. And you should think of the identity in our functions example. There's an identity function for every type, and the operation that combines thing we usually call composition. And composing with the identity doesn't change anything, and that's you'd expect. So turns out that a monoid. Monoids are particular examples of unremarkable categories, where a monoid is a category with one object. So things are trivially compatible with each other. They all fit together. And then once you say, well, there's only one object, then there's only one identity. That's your neutral element. And any two things compose.
And for that thing to make sense, you need to add some restrictions, right? So when you're composing, it should be associative, just like with a monoid, you don't care which way you grouped the crushing. Here, you don't care which way you group the composition. And then, well, the unit should be a unit. So if you're composing on the left or on the right, it shouldn't change anything. So here in the case of dominoes, I guess this is where it sort of breaks down, or at least if the notion of equality you're using is syntactic equality, if you tack on an identity at the end, the path got longer, right? So it is observable that this is different from, well, apart from the fact that this doesn't compose, but you have an extra tile. So then your notion of equality would need to disregard the path you took, basically. So it's not quite propositional equality, and then you recover the idea that everything is associative, identities are neutral, and so on. So as always, when we say things are the same, you could take the obvious approach, which is to say, I'm going to stick with equality that's provided to me by the system, or you could decide to be a bit more refined in the way you're picking your notion of equality. But here, to make things simpler, we're just going to use equality, propositional equality. Okay, so what did we say we needed? We said we needed a type of objects and a type of morphisms. So I'm going to use O as the type of objects. And here I've made everything level polymorphic because we'll see examples that are large. But basically what this means is that we're parameterizing the definition by the size, morally, of the carrier of the object, and then the size of the morphisms. Yeah. But you can more or less ignore it. It's
a thing that happens is that, if we're building categorical structure, sometimes the objects are big things like actual types, right? Sometimes the objects are very small things. So
like units.
Yes, like elements of the unit type, right? Mm-hmm. Sometimes O is unit, sometimes O is set. Mm-hmm. So we have to be ready to live anywhere in the set theoretic hierarchy. Some years we can't be arsed and we just switch on type in type, even though that allows you to create all sorts of paradoxes because it doesn't get in your way. Looks like Guillaume's planning to be a bit more conscientious this year.
Yeah, why not? Yeah. Basically, as long as it doesn't get in the way, you can just like sprinkle these levels and then hope for the best. Why are these two levels different? Well, there's no reason why a priori they should be the same. So just make them different. If no constraint arise, like making the same, there's no reason you should force them to be.
Yeah. So things will happen. So you sometimes, so you usually find yourself, it's rare for objects to be small, but arrows to be big. But it does happen. It's quite common for objects and arrows to have the same size. It sometimes happens for objects to be slightly bigger than arrows. So our favorite example of types and functions, the objects are big, right? But an ordinary function type is small. But then next up, we think about type constructors as being objects with polymorphic functions as the arrows, and all of a sudden those arrows are now quantifying over types because they're polymorphic functions, so they're big. Right. So this is the nuisance, is that we really do have to worry about the objects and the arrows separately.
Well,
we love a bit of moo.
Maybe. Yeah. Sure. Okay, and then compose. Typically call them ST for source and target, but no, we have, or maybe S middle and then target. Oh,
yeah.
Yeesh. I should just deactivate that shortcut. No. So if we can go from the source to the middle and from the middle to the targets, then we can go from the source to the targets. Okay. So this looks like standard composition, but for all we know, this could be first order objects, like actual data rather than functions. And then we're just saying we have a way of composing these things. We'll see examples very soon, actually. And then we have some laws. So what do we want to say? We want to say, well, very easy. We can look at last week's. So we had our diamond, we are now neutral, and then we're saying if you do neutral on the left or on the right, it doesn't change anything. And here it's exactly the same thing. So let's do identity, if I can spell it right. So for source and targets and morphism from the source to the targets, if I have the identity, I don't like that name.
Yeah. I always worry that.
Or is it backwards? Do you want to do it the other way?
This is good. I would just put a hyphen before then or something like that, just so that it is harder to mistake. So you know it's infix. I don't like. I don't like ordinary words being used as infix operators because you're blindsided by that.
Okay.
Yes.
So if we do identity on the left, doesn't change anything. And then we have the same with doing identity on the right. Identity.
Yeah, of course, you should, if you're calling it and then, the name of the law should say and then rather than compose.
Yes,
Search
thank you. It's even the same length. Okay. So let's do our favorite examples then. What's your favorite example?
Well, my favorite example is a map. I mean, like an actual, but we can't do that so easily. Yeah, just fire up Google Maps and go, look, right? There's dots, right? They're the places, and they're joined by streets. Some of the streets are one-way streets. What makes a map any good, by the way, is that the structure of the dots and the arrows on the map correspond to the actual places and streets in the city. You know, the whole point about maps is that you're not walking around in the diagram, you're walking around in the city, but someone has arranged for there to be a structure-preserving map from the diagram to the city. Because cartography is the thing that goes in the other direction. But anyway, what is our favorite example?
Well, I think it might just be ACTA.
Yeah, just. Although I always think it's a mistake to name. Yes, okay, you can say set and you can say.
So this is large.
Oh.
Yep.
Oh.
If I can bring my guy in scope. Toop.
Yes, so it's got large objects and small morphisms.
Yeah, so this is what Connor was saying earlier, right? About. So our example, our objects, they're going to be large because we said they were going to be large. So if we say sets, or what this means is set 0, right? It's the set of small sets, then it fits into set 1. We're all good.
A set of sets that don't talk about sets.
And then what's the type of morphisms between two sets? Well, we get our hands on two sets, a source and a target.
You could do that left of the equal sign.
Yeah, if you want.
Come on.
I like the...
Yes.
It's perverse, right? Because it's not the same arrow.
Yes.
So this is the arrow from the lambda binder, but this is the arrow meaning functions between.
Yes.
Horrible syntax.
Yes.
Yes. Right. And then we need to be able to build identities. So if you have a given set, can you build a function from that set to itself? Well, I think Agda can. Oh, it even found the composition, maybe. Horrible names, though. Oh, and even the proofs. Okay. That's not quite good at that fast. I wanted to search in the whole, not
you're
globally.
You're missing associativity of and then.
Oh, yeah. Oh, yeah, because they were grouped some other way in the... Oof. Okay.
Yes.
Let's patch this. So if you have a source, a left middle, a right middle, and targets, and you have H. Well, I suppose they are going left to right anyways.
Yeah.
Right? So if you can go from the source to the left middle, and then from the left middle to the right middle, and then from the right middle to the targets, tuk, 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 then it doesn't matter whether you're going F and then G and then H, or if you're going F and then G and then H. Okay. All right. So now I'm missing a definition in there. Oop, oop, oop. And then. Oh no,
You
and
called it
then
ASOC.
ASOC. Okay. Right, so we got our identity function, and then we need to explain if you have a function from S to M to, and another one from M to T, how to go from S to T. But this we already know. So we get our F and our G, and we return G of F
Yes, you need a.
of X. We need our X also. This is the flipped composition because of our definition of n then, right? Moving left to right as opposed to reverse order.
Yes.
Okay.
We're diagrammatic, and that's why we call it and then. If we were doing it the other way around, we'd call it after. So we're always careful to specify.
So then we need to prove that composition is associative, but we already know this to be true. Okay, so that was bad actually, because now we don't even see the... Oh, okay. Even without introducing things, they're already reduced. So purely by computation, these things evaluate to the same thing. So we had already seen this earlier, actually. For identity, yeah, I feel like we've already done all of this when we built the endo-monoids, right?
Yeah.
Because the notion of diamond for endo was composition, and then the neutral was the identity function. So all of these laws we saw
Yeah.
were already true purely by computation, and then eta laws telling you that two functions are equal whenever they equal all like variables.
Yeah, and it's somehow kind of this is less annoying than the endomonoid because there are no rules about which things are allowed to be functions, right? Whereas for endo functions, we had to insist that they were functions within one type in order to persuade them to compose properly as a monoid, because we weren't allowed different objects. And now we are, so we can just have all the functions we like.
Yes. So that's the sort of obvious example, I suppose. It's the example derived directly from this intuition that you have a morphism between S and M. But there are more examples than that, of course, otherwise it wouldn't be super interesting.
That's good.
So, the first one I wanted to do is, maybe I shouldn't do it for NAT, I should do it for everything.
Well, let's
The
start with
discrete. Okay.
Right. So,
Discrete. So it's a category where everything is small. All right. The objects are natural numbers. And then the notion of morphism from M to N are just equality proofs between M and N. And so this is why we call it the discrete category, because basically, if you think about it, right, you only ever have a morphism between two natural numbers if they're equal, meaning that you only have morphisms from every point to itself.
right.
And everything else is disconnected.
So what we're saying is that the only arrows are identity arrows. There's nothing more interesting going on that joins anything up.
And so the graph structure of this category, it's always good to think about the graph, right? When Connor was talking about the map and so on, is that you will have points, so the objects are points, right? One for every natural number, and then none of them are connected. That's why we call it the discrete category, because everything is just isolated.
So yes, and of course, you don't just get a discrete category for natural numbers. Any type gives you a discrete category.
So we need to be able to build a path from a number to itself, but of course, by reflexivity, the number is always equal to itself. And N then, so if you can prove that S is equal to M and M is equal to T, then you prove that S is equal to T is exactly transitivity, which is not in scope. Unfortunate. Up. And then these things, okay, these things.
You need to do some pattern matching.
Yeah, but it's going to be annoying. Okay. Just brute forcing it, right?
Yeah.
So we have a morphism from one to the all the morphisms are equalities, so you can just match on them and we're fine.
Yeah, except that you will need
Uh,
to name something somewhere because you've got lots of implicit things.
well, this is just true. And so the first one was just true because the definition of transitivity
Pattern matches on its first input.
Yeah, looks at its first
It's an
input.
arbitrary choice.
But in this instance, it's stuck on revealing the shape of M, so we can match on it. and then it just computes. And as Connor was saying, we can take any set, or in fact, we can take, oh no, what's going on? I never know how to bring back the editing mode. All right, parse error, fair. Oh no.
Yeah, you need to do it in a module. Okay, fair.
And there's nothing specific about the natural numbers. We can just do it for any type. Well, it's a bit of a white lie because we're proving equalities being equal to each other, but let's not go there. Okay.
It is important to see, we've mentioned that monoids are a special case. There's another special case of categories that we appreciate, which I think is probably about to happen. I mean, essentially, what we've said, you might have the sense that identity and composition are, when we do them in logic land, exactly the things we call reflexivity and transitivity. And there are an awful lot of things out there which have those properties. So in particular, any preorder, so we leave symmetry or antisymmetry up for grabs, but if you've got a relation and it's reflexive and transitive, you got yourself a category. So in particular, here we're in the situation where there's at most one proof of the relation. So this is the opposite to monoids, right? In monoids, there's one object, and all the interesting stuff is in the morphisms, in the arrows. For preorders, it's the other way around. There's lots of objects, but the proofs that they're related, there's at most one of them. There's no interesting structure in the arrows. They either exist or they don't, is what we're saying. So,
yeah, so for the identity, so our objects are natural numbers, and our morphisms are proofs that the first one is less than the second one. So for identity, we need to prove that a number is always less than itself, but that's trivial. Well, trivial, proved by induction. And then for transitivity, and then it's exactly again transitivity, which we saw earlier for propositional equality, but now it's for this relation.
Yeah. And then,
okay.
Does the library give you the?
And then associativity. Yeah, so I need to remember what it's called.
Yeah,
because I haven't imported it. Well, let's go look for it, actually.
Yes, go see, because you're hoping that you're going to get proof irrelevance, and that's just going to do it by brute force. If not, you can prove that it's proof irrelevant.
Right, so here I did Control-C, Control-Z, which allows me to look at all of the definitions in scope. Or rather, I did Control-U, Control-C, Control-Z, because I know the standard library uses a lot of aliases for all sorts of structures, so I want to normalize the types before I go look for these names. So I'm going to talk about equality between proofs. So I want to look for this relation and also equality. And then hopefully it's going to come up with some stuff. And it might even come up with the right thing eventually.
There's something, but it looks like you've got some chance of having a thing called less than or equal to irrelevant.
I would hope so, yeah.
Yep, I think you just went past it.
Right, it's here.
Yeah.
So let me just show you another thing. If I do the same Control-U, Control-U, Control-C, Control-Z, Z is for search because Control-S is already used for solve. So if you already know that you're going to get irrelevant in the name or something, but you can't remember exactly what it's called, you can also filter out by using some strings that should be substrings of the full name So sometimes it are irrelevant or whatever. And we can see that we have our guy here, and we also have the strict version above. Okay. So now that we know that these proofs are irrelevant, I mean, it doesn't even matter how you came to them. Oh, I need to import it.
Yeah, you do.
Doo-doo-doo. Oh, surely. Yeah, there we go. Okay,
Yeah, you just mash it.
nice. Okay.
Yes. So we're saying that these inequality proofs are so boring. The only interesting stuff is above here.
Mm.
Yeah.
Right, so, and as Connor was hinting, we could, just like we transformed that for discrete, so you talk about any type, we could talk about any type and relation which happens to be reflexive, transitive, and proof irrelevant, because that's the three key things you need. And then you can always build a category from that, where the objects are the elements of the type, and then the morphisms are the proofs. Okay. So maybe, should we do Kleisli now?
Yeah. Yeah.
So we can't do it in general, but we might be able to do it for this. Just.
What's that mean?
Yeah, thank you.
Yeah.
Okay. Kleisli. So what's the point here? Well, the idea is that we have this structure, right?
Let's just say Kleisli is the name of a mathematician who
Yes.
came up with this particular formulation of how monads fit together in a sensible way.
Yeah, so the idea of like the structure is clearly that we can always compose morphisms. So we can chain computations, right? So in the case, I didn't want to say it this way originally, because in the case of natural numbers and proof of less than, you're not really chaining computations because all the computations are boring, the proofs are unique and so on. But you can also see it as a way to chain computations. Like if I know how to turn an S into an M and an M into a T, I can turn an S into a T, right? So when you're doing computation in a monad, you're also training computations with all of the side effects encapsulated in the monads, and you're using that composition operator, binds, although bind is really talking about the endpoints, right? You're always looking at the result of the maybe, binding the results, and then describing some more stuff. And now we are going to see a more like composition-based definition of what it means to have these monadic computations. So and that's why I wanted to have the explicit levels
Yes.
again.
So again, large objects, small arrows.
So, okay. So if you have computations in the Mamie monads, the objects are going to be sets. They're like the set of the things you're computing. And then the morphisms, well, if you have a source and a target, so for the standard Agda thing, we're just looking at total functions from S to T. But now because we want to sprinkle a bit of monadic effect on top, we're going to look at functions from S to maybe T. And in practice, this could be any monad you want, right? Yes. Or rather, there's a Kleisli category for every monad. Internally, you still have a single monad because you need to be able to define this composition operator, and you only have bind allowing you to chain these computations if all of the computations are talking about the same monad.
Yep.
So let's start with this one maybe actually. So we have our what should I call it? First, or mm, mm,
yeah,
just giving up.
start and finish.
Yeah.
Yes.
Okay.
Yes.
So we have two operations, both of them may fail, and we have our starting value as our source value. And of course it's clashing now, so let's rename it to X. And there's not very much we can do, right? We can feed X to start, but then we may not get a value. So we need to unwrap that maybe value to see whether we got an M. If we didn't, we fail. If we did get an M, then we can call finish. And of course, this is all done via using the existing binds. Okay. And then the identity, well, for any object O, a set, we need to be able to go from O to maybe O. So this is just the return of the monads. I don't know if we have pure return here as a, okay.
Yeah, well, anyway, you would say just, I suppose.
So in this instance, we can just say just.
That.
And then if we look at these, okay, they look a bit horrible, but let's not get scared.
Oh, you're going to want those on the left, I can tell. And you're going to want your...
Yes.
Okay, so here we're going to need function extensionality.
Yeah, it's not showing us the parents, but this is going this way, right?
Yeah.
Because this doesn't make sense. Like we have two functions, we cannot just have them as a bind. So we're doing f of x and then g and then h. And here we're doing f of x and then g and h. And so this should look to you like the usual law we were talking about last year, actually, for monads, right? We were saying bind should be morally associative, meaning that as long the only thing that matters is the order in which you're running these computations, these effectful computations. The grouping, we don't really care about, actually.
Yeah, so that's more or less where it comes from, right? The monad laws are exactly by design the things you need to make this notion of composition give you a category. That's where it comes from.
Okay, so if I try to do REFL here, just like I did for the ACTA category, right? Well, the problem is that these binds are defined by actually inspecting the contents of the first value, right? So they're stuck. They're not computing away. So we need to actually get our hands on X and inspect it. So here, there is no, well, actually, maybe I can go back. Week 7, I think. On next. Was it week 8? Oh, was it week 6?
There was one, yes, where before we introduced the type-directed thing, there was...
Yeah, this one. So back from week 6, we grab functional extensionality. So the only way we can get our hands on X is to make equality a bit stronger and say that two functions are equal precisely when they're equal on all inputs. So if I do this and then I indent that whole block, right. Oh, right. I don't say which direction, of course, it's not going to be great.
Control X tab is your best friend.
And then, so here I can use next. Do I really need to say?
You should be able to live with it.
I'm going to hope that this is fine. Yay.
Right.
And now we can get our hands on X.
Yeah, and we're still in trouble. Right, because what you really need your hands on is f of x. You don't need that dollar. It's not Haskell.
Yeah, but I don't like it. I don't like this rule that the last argument can just have like a weird hanging lambda there. Okay, so we do want f of x.
Yes.
Uh,
You should pull this out as a, yes,
yeah,
exactly.
very annoying, but let's see. So for f of x, if we already got our hands on f of x, we want to prove this. With the space between f and x removed. Okay. So now I get to actually look at, okay, this is not in scope.
Yeah.
Should always import all the constructors. Oh, okay. So if f of x is just, then we're on the happy path, and just feeding the value we got for x reduces enough that the two things are now equal on the nose. So we're really happy. And then in the nothing case, well, we've lost no matter which path we're taking. So we've returned nothing across the board. Okay. And now we need to prove the identity laws.
Hopefully these
And this one reduced enough that we don't even get to see what it is. But it is saying that if you use return on the left and then you have a bind and a continuation, it's the same as running the rest of the computation on the value you returned, which is again one of the monad laws. And so this one is equal just through sheer computation. And the other one is the other monad law, saying that if you're doing m of x and then you bind the results and you immediately return it, it's the same as just running m on its own. And this is again just the monad law, but now it's getting stuck because this bind is defined by inspecting the result of m of x. So we need to again do a little bit of for next and a little bit of abstracting over the result m of x. So we need to prove that m of x followed by just is the same as m of x, where we've already computed m of x. Parens. Oh. Implicit value. There we go. And then, well, we just split on m of x. If it's just, well, we have just bind and then just, and here we have just. They computed the same thing. And then if we have nothing, well, on the first hand side, we try to compute with nothing, failed, then return nothing. And on the right hand side, we return the original nothing. So computationally, they're not quite the same, but in terms of values of the results, they're exactly the same. Okay?
sounds good.
Mm-hmm.
I guess we've got 7 more minutes of science, so
I think that's a good last example.
right, yes. So there are a couple of things to think about here, right?
Okay.
Yes. So okay, every monoid gives a boring category. Let's make sure we've seen that.
Yeah, so what we said is that categories are fancy monoids. That is to say that basically if you forget about these things, you have a monoid underneath, right? Or rather, you take the monoid and then you're saying, well, I want to keep track of the input-output relationship, or maybe you're tracking some kind of invariance, right? So if you're not doing anything, it just m from wherever you were to wherever you are. And then if you're combining two values in the monoid, but they were like aligned, like the invariants are meeting in the middle, then you get to take the step and go from the source to the target. But of course, you can run it back and say, well, let's forget about all of these like fancy invariants. Let's just use an index that has no interesting values whatsoever. So monoid, it's a category, or
Well,
yeah, okay.
now there's a couple of things to say, right? There's a way to turn every monoid into a category.
Yes. Ooh, yeah, okay.
Yes.
Mm-hmm. Or
You're going to want that A, actually.
do I want to lift or I don't know. Well,
Lift is it's too much. It's monoid, I think, is better.
okay. I'm going to do it like that because, I mean, the A can be reconstructed from the monoid A, so it feels bad to take it. Oops. Wrong splitting. Disgusting. Okay, so that's the monoid, so I should give it a good name, M. Okay. And now the objects, well, they're the A, so I can
No,
either...
they're not.
What?
The objects are unit.
Oh, yeah, my bad. Yeah, that's what we're saying, right? We're saying we want to get rid of all of these indices because these indices don't matter in this instance. So the objects should be boring. There we go. And then we need to explain how we transform, or what it means to have a morphism between two values of type units, which means we need to give ourselves a set here. And I'm going to be purposefully defining this actually. So this is a nice little trick. When you have something blue, so type constructor, and you want to recover some of the parameters, you can just define a magic function, which grabs the parameter and returns it. That sounds outrageous because it's not actually coming from that value. But through unification, this parameter can always be reconstructed, right? Because this is a hard, like, blue type constructor. And so then you can be explicit rather than like binding A implicitly on the left or something. Say, my set is the carrier set for that monoid. And this way you're documenting your codes a little bit. And then for the identity, so you need to provide a morphism between any value of the unit type to itself, just to say, just whatever a value in the carrier.
Completely collapses to...
Ooh, yeah, that's annoying. It would have been better to do it in a module, actually.
Yeah, but yes, you wanna, because you want to locally open that thing.
Yeah, I do, but now I'm screwed. So
life is
yeah.
Right.
So we want an arbitrary value, but in the back of our mind, we remember that we have these identity laws, right? So that arbitrary value should be computationally uninteresting. And so we pick the neutral element because that's...
Likewise, when you normalize these types, you see you just want a binary operation.
Oh yeah. Yeah. If you run it, you want a binary operation on the carrier of the monoid. Well, lucky you, every monoid has a binary operation on its carrier by definition. Okay. And then you need to prove associativity. So, I mean, it's talking about the carrier, but it's very readable. Oh, no, it's not, because the M is getting, yeah, okay, it's disgusting. Because this is a two-place function, right? But because we have an open monoid, now it's three-place because it takes the M also, so everything is off by one.
Yeah.
But we still get to see that basically we have bracketing to the right here and bracketing to... No, this is bracketing to the left, actually.
Yeah. Yeah,
Yeah, I don't know that we can see anything, but
it's,
um,
we should tidy this up.
yeah, okay. Screw it.
I mean, possibly not this instant.
Hmm. A bit of magic, search and replace. Up, 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 up. Oops.
Yeah, you Odween. Yeah.
Oop.
And you need that thing, yes. And now you can say open monoid am. Thank goodness.
Oh.
Um,
All right, so it's a lot more readable now because things that should be taking two arguments are actually taking two arguments. So we can now see actually that the left grouping should be equal to the right grouping. And I'm hoping this is the right way around. Yes, good. And then identity on the left, new, blah. And then identity on the right, blah, new. There we go. Yeah, so we can turn any, right, this is the message, right? Categories are fancy monoids, or if you want, you have a monoid already, you can turn it into a boring category. Well, boring. Boring in the sense of the objects, but clearly the sense of the morphisms, they're interesting because you have different elements there.
yeah, so yes. Categories generalize both monoids and preorders, but in different ways. So here they generalize monoids by imposing some notion of compatibility, that things have to fit together to go together. And they generalize preorders by saying, well, there might actually be something interesting in these arrows. And yeah, that's how you find them all over the place, and we will.
Yep.